and welcome to the Austin Forum Upload, where we explore pervasive and emerging technologies and their influence and impact on society.
In this series, we upload direct to you information, opinions, and insights from thought leaders, experts, and creatives from Austin and beyond.
They'll share their perspectives through conversations, interviews, debates, discussion, and more.
I'm Jay.
I'm John.
And I'm Barbary, and we co-produce the Upload for the Austin Forum on Technology and Society.
I'm Jay Boisseau, the director of the Austin Forum on Technology and Society, and I'll be your host for this episode of the Austin Forum Upload. I'm pleased to welcome my friend and partner, Chelsea Collier, the CEO and founder of DigiCity, to be my co-host for this episode. Chelsea, thanks for joining us again.
Hey, Jay. Always love to co-host with you.
And Chelsea and I are going to interrogate a friend of ours today. Well, I'm very pleased to have on the show Worley, the founder and CEO of Strangeworks, and has a long career as an entrepreneur and innovator in Austin. So, Worley, thanks for joining us on the show.
I'm super excited to be here.
So, before we dive into quantum computing, Worley, why don't you tell the audience just a little bit about yourself and your diverse background?
So, started my career at Apple answering the phones, ended up working in R&D, left IBM, done a few startups, a few big corporations, and now I'm really focused on quantum computing and then on entrepreneurial programs globally that are focused on deep tech.
Great. And Worley undersold himself a little bit there, so let me brag on him a little bit. He founded Chaotic Moon, which was acquired by Accenture, and then Honest Dollar that was picked up by Goldman Sachs. And it seemed about 6 hours after you founded it.
It was pretty fast.
Like
it was on a 1-year anniversary, and then we spun a gaming company out of Chaotic Moon that was acquired by Zynga. And then, I'm trying for nobody to acquire this one. I'd like to have a job for a little while.
And of course, you're also famous for the taser drone.
Yes. Yeah. And the mind control skateboard. But
I
prefer the skateboard, but the taser drone is a lot more sensational.
I preferred the taser drone, but I wasn't the one getting tased. So, yeah. Great. So let's jump right into it here. We're going to talk about quantum computing today. It's going to be a topic that is every one of our listeners will probably have heard of, and almost none will know the technology behind it or even the implications of it. At the Austin Forum on Technology and Society, we don't talk just about the technologies, but about the societal implications. And so we're going to do some of both of that today. But first, really high level, what is quantum computing and why is it important?
So this is actually so much easier than people make it. So the way I like to think of it is imagine that you have a quarter and you're sitting at a desk. And you lay that quarter flat on the desk. If it's a heads up, it's a 1. Flip it over. If it's it tells up, it's a 0. Now, on that two-dimensional plane, it can only be in one of those two spaces. Now you take the quarter and you flip it in the air. And when it's spinning in the air, is it a 1 or is it a 0? It's in a superposition of both 1 and 0 and a whole bunch of things in between. So unlike bits, qubits are simply block spheres. They're atomic particles that are frozen or trapped by lasers or whatever technique you use to suspend them. And you can put spins on them on the y-axis and the z-axis and the x-axis and then like h and other quantum functions. So when you think about it, it's really simply a probability machine, right? So everything when you look at it, much like Schrodinger's cat, you have to have it select to a 1 or a 0. But in the time in between then, you can evaluate huge amounts of data and outcomes that traditional computers are incapable of. Think about it this way. In your laptop that we're recording on today can only do things we could do with pencil and paper. It would take us 100 years and it takes it a fraction of a second. Well, a quantum computer is really applicable when you have problems where you put a couple of inputs, and when you add just 2 inputs, the evaluation time soars. So it's not that traditional computers, or what are called classical computers, can't do these calculations. It's that it would take them hundreds of thousands or millions of years to do, and a quantum computer might do them in an hour or a few days or a couple of weeks.
I think that's a really good explanation, and it brings it home in a tangible way. The piece with quantum computing that I always have trouble with, and maybe there's no answer to this, is how does it make a difference in my life, just walking down the street, an average person?
So that's a great question. So if you think of everybody's focused on AI today, right? I believe you can't really have an artificial intelligence without having quantum computing because I believe the brain is quantum mechanical. Now, I've had that argued both ways by neuroscientists everywhere around the world over the last 2 years. But if you believe that nature is quantum mechanical, and if you believe your brain is, and if we're going to have a true AI that would help in all of the things in healthcare and digital cities and everything that we think about, then you need a quantum computer. You need the ability to do those types of calculations. But there's a lot of much simpler examples. when you're texting on your phone and it does the autocomplete and it says the wrong word and you send that to your boss or your boyfriend or your girlfriend or whatever, that's because we can only look at so many permutations of how you spell and I spell, et cetera, et cetera. So when you look at functions like that, it will affect things like that eventually. Why is Google interested in quantum computing? Well, search, right? Things like Grover's search algorithm. So you look at that and you say, okay, I have a phone book, classical phone book example. I have Chelsea's number. I don't have her name. I want to look with a regular computer. I look line by line by line. Well, a quantum computer would only need the square root of the number of entries to find the same answer. Right? And so there's a whole variety of things it can be applied to, everything from, quantum chemistry and kind of molecular science and material science to finance and oil exploration to building new batteries to not use as much oil. So really just think about that, ignore the hype and think about it as we have problems where the evaluation times take forever. And we'd like to not wait 200,000 years or 2 million years or 20 million years to get that answer. And that's where these computers will be, applied. And that's where they'll change society for the better.
Yep. Digitization on steroids.
So they're not good for all kinds of problems. So can you sort of talk about which classes of problems they're not good for compared to which ones they are?
Absolutely. The example I like to use is everybody worries about quantum computing breaking encryption, right? And to do that, you would use an algorithm called Shor's algorithm. Well, there's 5 steps in Shor's algorithm. The first one is it an even or odd number? The second one is it a factor 2 coprimes? The third one is we need a number to use in our calculation. And when you get to the 4th step, that's the non-deterministic order finding. That's the quantum computation. So if you think about it, I could write an iPhone app that could tell you if a number was even or odd and if it's a factor of a coprime and do it blazingly fast. It would be a waste of time and resource to do that on a supercomputer. So these, processors, and I don't believe they'll be computers. I think eventually you'll find these will just be like a GPU or a TensorFlow processor, a TPU. You'll have a QPU because they're only good for computational complexity. So that's why, at StrangeWorks and several quantum companies, the way the software works is you can program anything you want, do what's called full program execution. So you can run the classical part, and then you find the computational complexity. You use the quantum processor for that, and then you bring it back in and you continue. So, it's not that they're not good for any problems. People argue that they're only good for, aerospace and energy and pharma and finance. And I would say they're going to affect gaming and communications and the internet and everything. Anywhere that you have a computational complexity, so an NP plus problem, NP plus hard, BQP, or where the evaluation time soars. And maybe we should give, the listeners an example of a problem that they can easily
you're jumping into NP hard problems. I'm not sure all the listeners are going to know what that is.
So let's put it into perspective. Let's say that we want to send Chelsea to 14 cities to talk about
that's just a regular week for Chelsea, actually.
I was going to say that's today, right? Okay. But we want to look at what is the optimized route for her to travel with a whole set of variables from the airline or the bus to the traffic lights downtown, et cetera, et cetera. And so when we look at that, your laptop probably does about 10 to the 9th, calculations. It's about 10 to the 11th problem, about 1,600 seconds. Your laptop could tell us the exact order of operations. Where should we go? What's the optimized path? What's the best way for her to travel here and there and everywhere? Now, let's say we want to send her to 22 cities. The complexity doesn't go up that much. The number doesn't go up that much, but the complexity increases exponentially, meaning that same computer takes 1,600 to 2,000 years to give us that optimized path. So when you have those situations, that's where you want to apply quantum computing. And those situations pop up everywhere, right? They pop up in imaging, they pop up in, neuroscience, they pop up in chemistry. So, but that's the kind of problem set you're looking at. It's not there's one thing a quantum computer is good for or there's things it can't do. It's that these things are built for complex calculations. Anywhere that you have a complex calculation, you can potentially apply a quantum algorithm.
So it sounds like you're saying that once these things are feasible, they still won't be cheap. So they'll be used more as accelerators, just as we use GPUs now. A GPU in a server is an expensive part of that server. So you only put GPUs in that server when you've got codes that are complex and numerically intensive enough to justify that cost and make it a good return on investment as opposed to wasteful.
And I think it's an important thing to realize for the non-techies, because non-techies are used to kind of evolution and replace, right? To me, it sounds like this is, yes, an evolution, but it's not a replacement of current technology, air quotes, that nobody can see. It's simply applied to the places where it can be most maximized.
Well, this is why I don't like calling them quantum computers in the traditional sense, because what people imply is that your classical computer goes away,
right,
and you have a quantum computer. And the fact is it's a marriage of the two, because every quantum computer has either the laser systems or cryogenics or something, and those are all managed by classical computers. Like when you look at a D-wave, which is one of the best known examples, even though physicists will argue whether it's truly quantum or not, it has a big black box and there's a little black box off to the side. That's where the classical computer is that manages it. What you're doing is you're taking the data from the classical computer, in that case, putting it into a system that freezes, lowers the temperatures lower and lower all the way to absolute zero. And you put all the information down in there and you do the processing, and then you pull the answer back out onto the classical machine. So these things are interdependent. And to think of it as it's going to change everything, there's only going to be quantum computers, is a little bit ridiculous.
Sure.
So we should probably let the listeners know we've talked about it like they're here and they're an option. But there are not very many quantum computers of any type in the world. They're different types. They're really expensive and they're hard to build and they're finicky. So
what does expensive mean?
Well,
are we talking millions
the
of dollars?
last time I
billions
asked Santa
of
for a
dollars?
D-Wave, it was about $10 million, I think. Is that right?
They may have that down. So you can access a D-Wave right now for about $2,500 an hour. So there's moving to a cloud-based model, as most things are. But you have to look at these different quantum computers. And the thing you have to remember, two things to your point. Number one is an annealer, probably good for optimization, probably gives you the answer that's the right answer, probably most of the time. But then you run the calculation a bunch of times and kind of average out and figure out what you're looking for. Circuit gate models, this is what Google and IBM and Rigetti are working on. Those work a little bit more like you think of a traditional computer working, right? There's gates and operators, et cetera, et cetera. And then you have ion traps, which do work in a similar fashion, but use a completely different physics. You have topological, which is what Microsoft's working on, that will probably win them a Nobel Prize one day. It's extremely advanced science, and they'll tell you ooh, it'll be here in the future, right? They don't even set an expectation. And then you have about 30 other ways you can build a quantum computer, and some of them are super cheap, and some of them are really expensive. Building a qubit, adding qubits is not hard from a hardware perspective. Adding qubits, going from 1 to 2 and 2 to 3 and 3 to 4, without the noise level becoming completely so much signal to noise, is just completely out of whack that you cannot get an answer out of the machine, that it becomes unusable. That's the problem, right? The Achilles heel of quantum computing isn't that we don't know how to make more qubits. It's that we don't have the techniques, the software, and the hardware to keep the noise compressed so that we can actually see what's going on in that quantum system.
So you want to tell our listeners what people have to do to try to keep the noise down? Most of these systems are super cool.
They're super cooling. There's a lot of cryogenics. There's using ion traps for lasers, but the main thing is they're shielded in every case in a dilution chamber or giant box or both.
We're being serious right now.
Yes, from all of the environmental effects. If you open up a D-Wave, a box, I don't know what their latest machine is, but let's say roughly 8 to 10 feet by 8 to 10 feet for one of their previous models. When you open that up, inside is a chandelier of cryogenics that goes down. At the bottom is the chip, and at the top is the largest ring. And the largest ring is probably only a couple feet in diameter, right? And everything else in there is specifically designed to prevent gamma rays and the flotation. And a lot of these computers are suspended if you go into the labs, so that the movement of the Earth and this and that. I mean, they're extremely fragile systems. And so, back to your point, the way I like to get people to understand it is, I don't think we have quantum computers. Right? I think we have really good equipment for exploring the quantum landscape, and we have a fundamental architecture on which a computer can be built. But without the noise control, without the environmental stuff, getting cleaned up, then, it's not going to be a laptop, and it's probably never going to be as reliable as your laptop, or in a laptop, or in a smaller format. They're probably all big format machines for the foreseeable future that are housed in data centers and accessed via the cloud.
So let's take a real quick, super off-the-road tangent. So how does this result in economic development for geographical regions that are maybe not the quote-unquote hotspots? And where I'm going with that is the frozen tundra. Is that the new bastion of innovation? Or does it matter?
So when you think about that, the thing that my mind immediately jumps to is it's more like, how are these things going to be developed in a democratized way? Not because of the, economic development that they could create in building machines or learning how to program them, et cetera, but in the fact that this is the new space race. This is an arms race, is how it's seen by many countries. You're talking about computational capability that you could completely devastate a stock market. You could create completely new forms of weapons. You could do new aerospace, radar, stealth. Like, there's so many things. And so there is a race going on with countries all over the world. Sweden, the US, and Chinese are dumping tens of billions of dollars into this research. So I don't look at it from like, where's it going to create economic development? I look at it from like, how do we democratize the technology in a way that it doesn't become all of a sudden the complete global power structure changes or things like that.
Is that possible? Are we capable of that as humans?
No, probably not. But I mean, it's worth trying, right? Like,
I like optimism.
I'm trying to remain very optimistic about it. Although sometimes I'm looking at it and it's like, wow, what But here's the good news. If I had a 1,000,000 qubit machine right now and I dropped it in the middle of Tokyo or San Francisco or New York, there would be nobody who knew how to program it or take advantage of it, right? One of the things we're skipping that we need to be very realistic about is, in our haste to build a quantum machine, we haven't stopped to build a quantum workforce. And so there is an opportunity for everyone around the world to look at, how do they build that quantum workforce? How can they educate their own society on how to program these machines or how to use them? And I think that, you see countries doing that, but you don't see them doing it in enough of a way. I mean, even in the US, there's not enough quantum computing programs in universities, for example. And we're, arguably one of the leaders. We were a little bit behind. We've been catching up. I put us in 11th place 2 years ago. I'd say we're in like 5th place now, but, it could be argued.
The U.S. is in 5th place. So I was going to ask you that. Who are the leaders in quantum computing? And I mean by technology vendor, by country, however you want to rank them. How do you look at that landscape right now? Who's in the lead?
Well, so while all of the big companies would hope they're in the league, Google, Microsoft, IBM, everybody, they're all kind of on this even playing field where this is a completely new area of science, right? So they can all hire the quantum mechanics experts and have their developers and everything, but the progress is going to be a little bit slow, and then it's going to take off, right? So obviously Microsoft, Google, IBM all have very good programs. I know people that work in all of those programs, and they're amazingly talented, and so they're kind of the leaders. Now, out of nowhere, Honeywell said, we've been built a machine, and has said that they will get revenue with that machine, and that machine will be available to enterprise before the end of this year. And they kind of came out of nowhere.
Wow. Now, I missed that, actually.
Yeah, and so then you've got D-Wave, right?
Built environment.
Right, and so then you've got D-Wave, so they're kind of the leader in annealing, right? So think about types. So classic, circuit gate machines. IBM, Microsoft, and Google are all working on something that can use those kind of principles. In the annealing area, in Japan, Fujitsu and Hitachi have come up with emulators. So Fujitsu's emulator, their new emulator, is almost as fast, if not faster, than actual D-Wave. Except instead of being millions of dollars or $2,500 an hour, it's going to be, maybe they'll sell you a 4-space rack mount unit for $20,000 or something or whatever. So there's a bunch of interesting stuff happening there. And then you've got PsiQuantum and IonQ and Alpine, which are all in the ion trap space, which are using lasers. So there's not really like anybody where you say they're the leader, but there is a group out of the 170 companies working in and around quantum in the hardware space. You say, well, here's kind of the big 3, maybe 4 if you include Honeywell. And then here's the kind of startups. D-Wave still counts as a startup in that space. And you say, well, really, there's not a leader, but there's like the 3 or 4 that you can watch.
Because it's a new and emerging space, most of the time when you're looking at new and emerging spaces, they start off as collaborative instead of competitive, just because you got to do it to get it off the ground. Because this is so private sector led, is it competitive from the start?
This is my favorite question so far, and maybe of any interview, because that's how everything I have ever worked in and around has worked. That is not how this works. When I go out for funding, I hear VCs tell me there'll be one vertically integrated quantum computer and they'll have all the software, so they don't understand why I'm trying to connect to multiple quantum computers. When I go around and everybody says, a lot of people don't know how I started StrangeWorks, but StrangeWorks came out of the frustration of trying to start a Linux Foundation project to get everybody to work together, to which bringing a lot of these companies into a room together in San Francisco to find out maybe they don't actually want to work together because it's a big prize. People are going to win Nobel Prizes out of quantum computing. Companies are not going to go up by billions of dollars. There are trillions of dollars of effects on every aspect of everything in the world, from pharmaceuticals and finance to, automation and, autonomous vehicles, et cetera, et cetera. So right now, I feel like we don't have enough collaboration and enough community. And so we've done a really odd thing. We have no financial, we have many financial limits. We don't have any, financial freedoms. And we're a small startup, but we've found that through partnering with like Stack Overflow and other people, we can build a lot of community resources that we don't manage. We don't mentor, but like are starting to gain traction in that. But it's going the opposite direction of what you just said, which is super interesting, because I kind of thought when we came out and said like if you say open source, people like open source and they're like consuming it and they're like doing it in certain areas, but it's an extremely competitive thing. And I compare it to being in a kitchen. Mm-hmm. So 3 of us are in a kitchen and we're fighting over a piece of pie, but the sprinklers are on and the oven's on fire and there's flour everywhere and just crap all over the place. And we're not anywhere near a pie yet, but we are very intently focused on fighting over that piece of pie.
That's a great analogy.
Yeah, I agree with Chelsea's assessment about that initial phase and how people tend to collaborate. But this is one in which, as you just said, the stakes are perceived, at least, and probably truly perceived as being so high that people are competitive out of the gates.
Absolutely. Extremely competitive.
Yeah. So we should probably talk just a touch more about the international competition than not just the vendor competition and the stakes for military. In my day job, which has to do with AI and HPC, I occasionally talk to certain kinds of customers that have certain kinds of concerns in this general area, and we'll leave it at that. But quantum should, just as it offers tremendously more computing potential, can make even those concerns look small in the things that I'm dealing with in AI and HPC with traditional classical computers. So I know you must be talking to people who have great concerns about national security and what happens if one side has a tremendous computational advantage over another?
Well, as technology, and if you think of it, computers and this ability to calculate things invades every part of our life, then yes, there's obviously, if you think of the NDS, the National Defense Strategy, or what the U.S. is trying to do with multi-domain, operations and all the sensors in the world to tie into things, then yes, it becomes a super big issue. The main issue everybody focuses on is encryption. And so I have good news and I have bad news. And the bad news is quantum computing will break encryption because encryption is dumb. The way we do encryption is we make it where you need a lot of resource and a lot of time. So you need like 300,000 years and millions of dollars to break this. And in the 40s and 50s and 60s and 70s and 80s and 90s and the aughts, this was an okay approach. As quantum computing enters the world, this is no longer a viable means of protecting data. And so that's the bad news. The good news is that people don't understand what the ramifications of it protecting that data is. So let's say that I have the ability to use something like Shor's algorithm in combination with a few things to take Chelsea's public key and derive what her private key looks like. Okay? That can happen. But that might take an hour or it might take a month. And I'm only doing it for her key. I don't go and instantly break all keys, right? So we have to kind of temper that fear and uncertainty and doubt with some reason. To answer your question, China has invested more than any country on the planet in this and in quantum communications and something called quantum metrology, right? So quantum computing is not the scary thing about quantum. Imagine that I had an alternative to GPS as a way to circumnavigate the globe based on gravitational waves. And I could then set off a nuke in low Earth orbit, and there's no GPS. And so I'm the only military that can circumnavigate the globe without using a sextant, right? And it's like, that is an incredible, crazy thing, right? And that's the kind of stuff we're talking about. We're talking about these huge, shifts that sound like science fiction that are actually science fact. And so China is probably the number one from an investment perspective. There's an argument about how much of the stuff they publish in state media is, how much, kind of like polish is on it and how much BS is there. And by the way, same thing for everybody here and everybody in quantum. The US recently passed $1.2 billion in authorizations in the budget, but people don't understand how budgets work. Everybody was like, great, we put in $1 billion. Okay, well, China was at $25 billion a year and a half ago. Okay. And they've been investing since the 70s. So if you go to any of the cool, you can search the CIA archives for declassified stuff. You can search for quantum in China and you can find stuff out where they're like, 1976, the Chinese are working with the quantums, So it's like, this has been going on. Quantum mechanics came in at the 5th Solvoy Conference in 1926, right? Fast forward, 82, Feynman and Benioff think about using a particle as a bit. And then Los Alamos in the early 2000s has 7, to 12 qubits, and then maybe you start getting to 20. Well, then in 2017, you went from, 5 to 12 to 20 to 50 to 72 to 128 stored qubit plan for Righetti's machine. The ion trapping machines, a couple of them that haven't come out publicly, but they've put it in papers and stuff. They probably got a couple hundred qubits now that they can play with. That curve is going up. Sweden invested 1 billion kronen in the space. Germany has investment in space. Israel has investment in space. Like every country has investment. To figure out which one of those countries rank and answer your question, it depends. If you look at it from investment, China is way in the lead. Right? That 1.2 billion we just talked about in authorizations, people don't understand how government budgets work. So they're like, great, there's 1.2 billion. Well, that's authorizations, not appropriations. So we can go steal that money from somewhere else in the budget, and then we have to go through the process of actually getting it approved and getting the money. It's not like there's 1.2 billion magical dollars available to quantum researchers. So I would say, finance-wise, China, Sweden, Germany, Israel, there's a whole bunch of companies ahead, and US is probably down 5th or 6th from an investment perspective.
At least it's not 11th.
That's a federal investment perspective.
It's from a
federal investment. A lot
investment.
of the companies that are leading in the space are U.S. companies, right?
A lot of the companies we
know of their progress.
We have this view where it's like, well, is it in Silicon Valley or not? Well, it's like Alpine in Germany is doing amazing things. I would question, and I haven't used their stuff, but just based on reading some papers and kind of discussing it in my community, I would question whether, is PsiQuantum and IonQ from here in the States, are they ahead of that? Canada, which is a country that I haven't mentioned yet, is probably from technically number one. Waterloo has had a quantum program for forever. Yeah. D-Wave came out of there. If I said from a technical perspective, where would I go look for talent, or where do I think, ETH and Zurich in Canada are probably, 1 and 2. And depending on the criteria, you could probably interchange them in those positions.
So I'll throw out a bold question that may be impossible to answer. Do you think the U.S. needs to wrap its economic and education and even how they manage government budgets around the need to lead in quantum? Should it change everything? Is it the game changer?
In the last couple months, I've spoken with DOD and DOE and Senator Jack Reed and the Senate Arms and a whole bunch of people in there. And I tried to run this. So a couple of years ago, I wrote a blog post on the U.S. needs a Manhattan Project for quantum, right? This is that level of importance and impact. And I think, and of course, I don't want them to just come take my company and move me out to a desert to work on that or anything. So
or the frozen tundra.
Just in case they're listening, which I know some poor, there's somebody at every government intelligence agency that has to listen to all these podcasts and read all of the blog posts and all of this stuff and write it down, take notes. And God, I just fear.
So you're getting it on the record now. You don't want to.
I do not want to do that. Okay. But I also fear what their interpretation of that with Feynman said, if you think you understand quantum mechanics, then you don't understand anything about quantum mechanics, or something, very close. I'm paraphrasing. I feel that way about quantum computing. It's like, if you're like, I absolutely totally understand that, it's like, you clearly have not been working in this space.
Then maybe I understand. I was telling a friend about this podcast before this, and I told him I got an A+ in quantum mechanics 2 at UVA, and he thought I was bragging because he didn't let me finish. I said, no, hold on. It was the class I understood the least about. Got the best grade in it. And at the end of it, I thought all I knew how to do was solve some mathematical problems that appeared on tests, and had no innate understanding. I didn't feel like I truly understood.
Maybe the professor didn't understand it either, which was
the
gold
could have
star.
been it too.
Yeah.
Well, it's like with quantum computing. It's like, oh wow, there's a lot of linear algebra, and then you're just like, oh, and then all the other stuff. Yeah,
that's right. Okay, so we've had a good discussion about what quantum computing is and why it's important. What do you see as the challenges and roadblocks? Is it just funding? Is there more basic science? Is the need for cooperation such that it's holding us back? What are the big roadblocks right now?
I think collaboration is needed across the space, the software and the hardware and everything. And that's going to be hard to get people to do because of the, incentives that system and the way it's set up right now. Funding is a problem in certain areas. It's not a problem in others. But I think really we're still missing a lot of fundamental science we need to move from kind of where we're at to where we want to go. So right now, John Preskill and a bunch of other people have said we're in the noisy intermediate quantum space. So meaning that we're going to have like these rough quantum machines and we can kind of do stuff on them, and that we work through these different phases, and eventually we have a general purpose quantum computer. So I think collaboration is important. I think funding is important. I think the biggest thing missing is a quantum workforce, people to work on the machines and advance the machines. I mean, if you think of any other industry, telco, silicon, et cetera, we had workforces and we trained workforces into these emerging industries. I don't see enough of that going on. That's probably the biggest thing in my opinion.
It sounds like that's one of the major takeaways, at least for me as the non-techie at this 3-person table. We're trying to still introduce STEM in schools. So the big question for me is this an everyone challenge, or is this the special techie smart people's challenge and it needs to be a very specialized workforce? Or do you need the entire educational system to change globally?
I wish the entire educational system globally would change. So I'm going to say yes to that. I think, we wrote a book. I wrote a book with Chris Ferry called Quantum Computing for Babies. And the idea behind that book it's like funny, haha, but the idea was like, we should start teaching very young people about this amazing area of science because, like you said, you went to UVA and you did this, you're like, I made these great grades and I still don't understand it. It's like, we've got a lot of years of that, in my opinion, coming. And so we should have, I did a program, for my Eisenhower Fellowship, which is to work with Germany and Japan to put quantum computing not just in the first part of computer science in colleges, but into like the super science high schools in Japan and into high schools in Germany, et cetera, and here. Because I think we need to drive this more complicated stuff, down fast. It's great that kids are learning trigonometry in, 9th grade or whatever. And that's useful, math is the language of science and it's all great, but there's a lot of things that we don't know anything about, and how the best way to learn about them is through teaching. So I think we need that curriculum, throughout the school. And that'd be probably one of my biggest ones.
Great. So we've talked about, the workforce and the ability to stack the pipeline around that. We talked about the need for funding and for that to be a bit more flexible. What are the other kind of big takeaways? One more before we wrap up.
I think it's about understanding that how everyone understanding in the general populace, how fundamentally different our world is going to be on the other side of this. How much this is going to change finding a cure for cancer, space exploration, energy, new forms of energy, new forms of targeted drugs and therapies. So many things are right just outside our grasp because we don't have the computational power to solve them. And so I think the more the general public gets involved, if you think the evolution of telcos, you're never going to have the general public contributing financially, but you have government funding for communications, and then you have some venture funding. And then eventually the way that things become like an iPhone is in your hand today is that there's billions of people spending money on this on a consumer perspective. So, I would like to see the first few phases that get going with quantum. I don't know that there's any of the consumer phase, but it's definitely something that will affect everyone's life in unimaginable ways.
Well, that's a great overview and a great final summary and takeaway point. So, great podcast. Thanks for joining us. How can our listeners learn more after this podcast? Where would you send them to help them start to become part of the quantum workforce, or at least to be able to appreciate what you just said?
Well, so there's a bunch of great videos on YouTube and also a bunch of bad ones. There's a good area. But I would say, you can watch some of the people in the space. It's very easy to find quantum computing videos from all MIT and Stanford and everywhere, and a bunch of the professors that are associated at Yale and Princeton, et cetera, et cetera. But we have a website called quantumcomputing.com that if you want to play with quantum computing, you can go and sign up. It's free. And we keep news up there, and we keep archive papers and things like that. And then we partnered with Stack Overflow, if you're a software developer, to create an actual Stack Exchange around quantum computing. And it's got almost 1,800 questions on it now. There's about 6,700 people there. And if you have a question, which is where most people start, is not reading about it. They're like, I have a question. You can ask it in that forum, and somebody will answer that question probably in a fairly expeditious time frame. And that's a good way, is I think, you can send people to books. You can tell them to go buy Quantum Computing for Babies, et cetera, et cetera. I think the best way is go become part of the community and ask the questions. Nothing wrong with someone going on Stack Overflow and asking a question about, I'm in an enterprise and I would like to know if it can do this, or, I would like to know where there's other resources or where I could get training. So I think those websites are probably some really good places for people to start.
So quantumcomputing.com, which
Right.
StrangeWorks hosts.
Yep. And then quantumcomputing.stackexchange.com.
Great. All right. So thanks a lot. That should help our listeners learn more. Thank you for being with us today, Worley. We really appreciate it.
Thanks for having me.
It's a lot of fun.
Thanks for listening to the Austin Forum Upload. You can listen to additional episodes and check out a schedule of our monthly in-person events at austinforum.org. The Upload is a production of the Austin Forum on Technology and Society, a nonprofit organization here in Austin, Texas.